NASA's Jet Propulsion Laboratory presents the Von Karman Lecture, a series of talks by scientists and engineers who are exploring our planet, our solar system, and all that lies beyond.
We are starting the straighten up and fly right maneuver, where the spacecraft will jettison the entry balance masses in preparation for parachute deploy and to roll over to give the radar a better look at the ground.
Indicate chute deploy.
The navigation has confirmed that the parachute has deployed, and we are seeing significant deceleration in the velocity. Our current velocity is 440 meters per second at an altitude of about 12 kilometers from the surface of Mars.
Heat shield set.
Perseverance has now slowed to subsonic speeds, and the heat shield has been separated. This allows both the radar and the cameras to get their first look at the surface. Current velocity is 145 meters per second at an altitude of about 9.5 kilometers above the surface.
Nav filter converge. Velocity solution 3.3 meters per second. Altitude 7.4 kilometers.
Now has radar lock on the ground. Current velocity is about 100 meters per second, 6.6 kilometers above the surface of Mars. Perseverance is continuing to descend on the parachute. We are coming up on the initialization of terrain relative navigation and subsequently the priming of the landing engines. Our current velocity is about 90 meters per second at an altitude of 4.2 kilometers.
OVS valid.
We have confirmation that the lander vision system has produced a valid solution and part of terrain relative navigation.
Priming. TBA is nominal.
We have priming of the landing engines.
Back shell set.
Current velocity is 83 meters per second at about 2.6 kilometers from the surface of Mars. We have confirmation that the back shell has separated. We are currently performing the divert maneuver. Current velocity is about 75 meters per second at an altitude of about a kilometer off the surface of Mars.
TRN safety Bravo.
We have completed our terrain relative navigation. Current speed is about 30 meters per second, altitude of about 300 meters off the surface of Mars. We have started our constant velocity accordion, which means we are conducting the sky crane, about to conduct the sky crane maneuver. Sky crane maneuver has started, about 20 meters off the surface.
We're getting signals from MRO.
Tango Delta.
Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the signs of past life.
Hello, and welcome to another edition of the 2021 Virtual Von Karman Lecture Series. I am Nikki Wyrick from JPL's Office of Communications and Education, and I will be your host for our topic tonight, Helicopters in Space. Many of you took the chance to join us on February 18th as we watched the Perseverance rover successfully land on Mars. With this landing, the helicopter, Ingenuity, has also arrived safely on the Red Planet. As a technology demonstration, the helicopter is set to test the first powered flight on another planet. It takes both ingenuity and perseverance to fly a helicopter on Mars. So let's take a moment to see what this duo will look like in action. Wow, just incredible footage we have there. Joining us this evening as co-host is Sarah Marcotte, Public Engagement Specialist for NASA's Mars Exploration Program. Sarah brings over 2 decades of experience at out-of-school environments, working to connect learners of all ages to current scientific research. Hi, Sarah.
Hello, Nikki. So my role tonight is I will be taking your questions from social media. So keep those questions coming in the chat wherever you're watching tonight. And I'm sure you're as excited as I am about the helicopter's first flight. So I want to make sure that you know where you can find out all the background information so that you'll be ready when Ingenuity lifts off the ground. We have a website, of course, which is go.nasa.gov/Ingenuity. Now, on those pages, you'll find all sorts of interesting things so that you can learn about this historic mission. There's beautiful animations. There's images of the helicopter as it was being built in the clean room at NASA's Jet Propulsion Laboratory. There's cool quick facts. There's a helicopter model, and there's activities for kids. So that's the best place to go to learn about the helicopter. And of course, when the helicopter sends back images that it takes during its flight, those images will be on that web page as well. So I'm excited to see your questions. I see they're already coming in, and I'll be giving them to our guests throughout the show.
Thanks, Sarah. Great ways to get involved. As always, if we run into any technical difficulties tonight or small failures, we ask for your patience, and please do stick with us. We'll get them sorted out as soon as we can. Remember, this is your space program. We want you to get involved. As Sarah was saying, please put those questions in the chat. If you're watching on YouTube, Facebook Live, LinkedIn, ask questions in the chat box, and our social media team will bring up as many as we can. And if you don't see the chat box, please make sure you refresh your page and it should be right there for you. Our first speaker tonight started his JPL career writing software for the Deep Space Network. He worked on flight software for the Curiosity rover and is now the Mars Helicopter Operations Lead at JPL. Please welcome Timothy Canham. Hi, Tim.
Hi, good evening, everyone.
Thanks so much for being with us tonight, Tim. Can you tell us a little bit about who you are and how you got to work on this project? And let's bring up image 3.
Well, first of all, I want to congratulate Perseverance in doing a great job in bringing the Ingenuity helicopter into a nice soft landing on the surface of Mars. So I worked at JPL for a number of projects over the years. I started in the Deep Space Network. I worked on the Cassini project. And most recently, before the helicopter, I worked on the Curiosity rover flight software. As a matter of fact, much of my software that I wrote for Curiosity is now running on Perseverance as well. So most recently, our group had developed a set of software that we've used on a number of projects internally. So I was asked to be the software lead for the helicopter. And we had a team of 4 or 5 programmers that put the software together and tested it. And since we operate the helicopter via the software, I was asked to be the operations lead to actually operate the helicopter once we got to Mars.
It's an incredible story of how you ended up where you are today, but let's talk a little bit about the helicopter. How do you build a helicopter that's going to be able to fly on Mars? And if we could see image 4, please.
Well, when you design a helicopter for Mars, you have to keep in mind the environment you're going to fly in. Mars has a very thin atmosphere, so we need to design it to be very lightweight. The blades are very lightweight, they spin very quickly. And also, because we are so far from Earth, you can't have a joystick and just fly it like you would a drone at home. We had to write the software so that it could fly itself. We basically get it a set of instructions, and the helicopter takes off and flies to the places we tell it to. And we had an extensive test program here on Earth where we did many flights in a special chamber at JPL to prove that our software would work when we got to Mars. So we're very excited to be finally here and actually able to execute these flights on the surface of Mars.
It's incredible, and I can't wait for the chance to see all of that. We're actually going to bring the audience in right now and let them ask the next question for Tim. So, Sarah, I'm sure they're excited out there. What are they asking?
So Alethea on LinkedIn is asking, what is one of the greatest challenges of piloting a helicopter in space?
Well, as I mentioned before, the atmosphere is super thin, and so you can't design a helicopter like you do on Earth. And so we had to do very new kinds of algorithms in the software. We had to design hardware especially for flying on Mars. And so all of that was challenged. We did things that have never been done before. It's sort of a Wright brother moment in that we get to go to a planet somewhere outside of Earth and try a helicopter there that's never been tried before. So we had to do special design work and special testing to make it happen.
Sarah, let's do one more question from the audience for Tim.
Sure thing. I like this one. This is from Margie on Facebook, and she's asking for her 9-year-old son, Jonah. So we've got a young space fan out here. So he says, how will Ingenuity fly in the different gravity?
Well, that's a great question. And we designed it to be lightweight because Mars has about 1/3 the gravity of Earth. And so we had to design that in when we did it. It's actually too heavy to fly on Earth. And so we had a special mechanism when we tested it here on Earth that would pull up on the top of the helicopter and simulate Mars gravity. So we could fly in a chamber that was pumped down to Mars pressure and have a special mechanism that allowed us to simulate the gravity of Mars and let it fly around in the chamber. So yes, we had to keep in mind the gravity of Mars when we flew it.
It sounds like a lot of testing went into this project, and thank you, Sarah, for that great set of questions. Now, as Tim, you alluded to earlier, the helicopter, of course, had to get to Mars somehow. So joining us now is Perseverance Mars 2020 Systems Engineer, Dr. Farah Alibay. Hi, Farah.
Hi.
So this next question is actually for both of you. What are the challenges of working on a mission like this, separate but united? Let's pull up image number 5, and Tim, why don't you start off?
Well, as a research project, that's how we started. And so when we were doing all of our development and testing, it was a very fast, rapid, high-paced environment where we would make changes, we'd fix something, we'd try it again. And when you go to a project like the rover, the Perseverance rover, everything is very structured and very regimented with lots of processes you have to do. And Farah has been a great harbor pilot. I call her our harbor pilot. She guided us through all the icebergs of big project land to get us on the rover and to help us figure out how to run all these things together. And it has been a challenge because we've all been remote with COVID, and working together with Farah and the rest of the team has been a real learning experience for us.
I'm sure it's been a great learning experience too. Farah, how about for you?
Yeah, I mean, as Tim mentioned, one of the craziest thing is Tim and I have actually never met in person. So I joined the team, I've been on the Perseverance team for a long time, but I actually only started working on the helicopter right around launch when we really started thinking, well, this thing's on its way to Mars. We better figure out how to operate it. And so I was brought along and we were deep in COVID, and I've been interacting with the team remotely. And it's crazy because I feel like we've become close friends, even though, we've never actually physically met. But one of the challenges with helicopter is, unlike other instruments, for example, on a rover, typically we're used to bringing the instruments with us wherever we go. Whereas with Ingenuity, for the past few sols now on Mars, we've been looking for a place to drop it off, right? We are looking for a flat environment where we can leave the helicopter and then an area for us to watch it from and take those videos, because, if you don't have a picture, it didn't happen. And so it's a little bit unique in that sense that, it's a different mission. We're bringing it along with us. It has its own needs, and we have to help it figure out, we have to help it achieve its goals. And that's really what Perseverance is there for this particular tech demo is we are there to set the stage for the first flight on Mars, and help our friend achieve its mission goals.
I mean, what a great example of teamwork, especially during the times of COVID. Tim, we're going to come back to you in a little bit for some more questions, but right now we're going to keep chatting with Farah, who has been a systems engineer at JPL for the past 7 years, working on several missions, including the InSight, Mars Lander, and Marco CubeSats. Today, one of her roles on the Perseverance mission is to lead the operations interface with the Mars helicopter technology demonstration. So Farah, you've had a pretty exciting month. You're living on Mars time right now. Can you explain what is Mars time and why are you on it?
Yeah, so it's currently about 8:45 a.m. for Perseverance right now, which, well, so it's not 8:45 a.m. for me, but what I do right now and what the rest of the Perseverance team is doing is that we are working during the Martian night, and that's what we call Mars time. So our rover is too far away from Earth, and so we can't just command it. It's not like we sit behind our desks with joysticks driving the rover. I wish it was that way. Mars is way too far. So when we send signals to Mars, they're radio signals, they go at the speed of light, but it's so far away that it takes about 13 minutes right now for a signal to get from Earth to Mars, and then another 13 minutes for it to get back. So it would be a really long and boring day if we were sending a command and waiting each time for an answer. So what we do instead is that each night, the rover sends us information. It sends us images, it sends us data, it tells us what it did that day. We as a team analyze it. So we go into work at about 6 p.m. Perseverance time every night. And then we analyze the data, we prepare a plan for the next day as a team, and then we send it back up to the rover. And we send it up before it wakes up in the morning at about 8 a.m. So we work the Martian night shift, right? Which, okay, that seems fine. You just shift your schedule. Well, it's not that easy because a Martian day, which is, we call it a sol, is actually about 24 hours and 40 minutes. So it's just a little longer than Earth. So even though I start my day at the same time on Mars every day at about 6 p.m. every day, my start time on Earth shifts by 40 minutes every day. So this morning, for example, my wake up time was about 4:30 a.m. Tomorrow it'll be more like 5:10 and so on. So we're coming up this week and next week. That's why I was able to join you today in days where the Martian night is lining up with the Earth day. But I just came out of doing the night shift of having to wake up in the middle of the night. So it's just a shifting schedule. And we're doing that for the first 90 days of the mission, because those are critical times. We need to be working every single day on the rover to get everything checked out, to get the Ingenuity mission done, all of those key activities that everyone's so excited about.
I mean, that's definitely a lot of dedication that y'all's team are putting into this. As we saw before, the rover has safely made it to Mars, and that video is just incredible watching it land. I never get tired of it. Can you explain your role in relation to the helicopter mission? And let's pull up image 6.
Yeah, so as Tim mentioned, my job basically is to help accommodate the helicopter tech demo. So, and there's really two parts to this. Right now, you can see in the picture, actually, the helicopter is tucked in under the belly of the rover. It's actually horizontal below the rover. It's connected, right? It gets heat, we can communicate with it. And we have to deploy it on the surface of Mars. So in the upcoming weeks here, once we find a site that's suitable, we are going to go through a deployment process where we go from the helicopter being horizontal to going all the way vertical. And then there's the last day of our deployment is when we separate the helicopter from the rover. And what's special about that day is that from the moment that we separate from the helicopter from the rover, we have to drive off of it and expose the solar panels from the helicopter within 24 hours of that drop. Because if we don't drive off on time, if we have any problem, then there's a chance that the helicopter might not survive the Martian night, which is so cold, because it needs that energy from the solar panels. So my job has been to coordinate all of those activities, coordinate the rover side activities to get that deployment done, to drive off, to do all of the imaging during the flights, and to coordinate, for example, communicating with the helicopter. The helicopter can't talk directly back to Earth. It has to send its signals through the rover and then to Earth. So there's basically, I call it sort of a dance. There's a very careful dance that has to happen between the two projects. And I'm sort of the choreographer for those dances to make sure that everything happens. Everyone is right there when they need to be in order to have a successful mission.
That seems really complicated. And both you and Tim have talked about how this isn't like using a joystick to command these spacecraft. So how do you prepare for something like that? And let's pull up video 7 while you talk us through this.
So we test, and test some more. I can't tell you how much time I've spent in the Mars yard at JPL in the past few months. So the Mars yard is basically a big sandbox. It looks like Mars. You're seeing it in the video there. And we have a replica of both Ingenuity and Perseverance. The the replica for Perseverance is called Optimism. And we use those Earth robots to test before we get to Mars. And we test everything, all of the activities, all of the sequences, the timing, to make sure that once we do it on Mars, it's not the first time. It should be boring by the time we do it on Mars because we've done it so many times. So the video that you're seeing here, for example, is what we hope the deployment day will look like on Mars. So we tested our deployment and we tested driving off of it. And the other thing that we do is that we also test our people. So back in late January, we had a dress rehearsal for the day that we're going to drop the helicopter. So we had all of our team, in the control room, and I was sending them data and spoofing anomalies and things like that. And people had to react to them and do that go, no goes and decide, okay, are we going to drive off? Is the helicopter separated? What's the health of the helicopter? So that's really helped us build confidence in our ability to do this. And, I think we're as ready as we can be, and we're really excited to get to do it for real on Mars. It's a little bit like, when you've rehearsed for a show for a long time and then you're ready for prime time. I think that's where we're at right now.
I love what you said about this being a boring moment because you've tested it so many times that you want to make sure that it's going to work. And if it goes according to plan, I guarantee it will not be a boring moment for any of us. That's a great way to think about it. We're actually going to get the audience involved again to ask our next question. So Sarah, what are they asking out there for Farah?
Well, I'm struggling because there are so many great questions coming in. So I'm having a hard time deciding, but there are a couple themes emerging here, and so I thought these were really interesting. So for Farah, so Kurt on LinkedIn is asking, and it's also kind of related to what Alicia on YouTube is asking, having to do with the dust storms. So how will Ingenuity react to adverse environmental conditions such as dust storms? Will they work? Will the helicopter work in stormy weather? What do you think?
So we're not even going to try and fly in stormy weathers. One of the advantage of having Perseverance is that we actually have a weather station on board the rover. So we have wind sensors, we have temperature, and we've actually been very closely watching the temperature and the winds since we landed. We actually had a meeting today where we looked at the results that we have so far to try and see, okay, not just is there anything going on Mars right now, but even what time of day do we think it's better to fly? The winds on Mars, as it turns out, are really predictable. So from a day-to-day basis, there's times of day that are more windy than others. So we're trying to evaluate right now, okay, what are the patterns starting to look like, and when do we think that we want to fly to avoid sort of the gustier times of day? So yeah, we came prepared with our own weather station in order to figure that out and give us the best chance at success.
It's always good to be very prepared. I think we've got time for another question before we move on. So Sarah, is there another one out there for Farah that we could ask?
Sure. So Alethea on LinkedIn is wondering, how do you balance a lightweight helicopter with a helicopter that can endure an impact? I guess maybe when it comes back after a flight. So how do you balance those two things? Got to be light, but it's got to be strong.
Yeah, I mean, that's all part of the challenges of designing things for Mars, right? Is they have to be robust for the environment, and they also have to be, meet constraints like light in this case. So I'm sure that Tim could actually provide a lot more detail into exactly how the helicopter was designed. But I can tell you that with anything in engineering, there's a lot of cycles of iteration, right? We start with a design, and then we test it out, we try it again until it meets those requirements. That's true for the helicopter. That's true for the rover wheels, for example, right? We redesigned the wheels on this mission, and we tested, dozens of different types of wheels in order to get there. And I'm sure it was the same story for the helicopter, but maybe Tim can add a little bit of information here.
Well, sure. Thanks, Farah, for the intro. So the helicopter was designed to be both strong and light. So it's made of carbon fiber in many cases, which is really light but really strong. The blades can spin really fast and lift the weight of the helicopter, but if you picked one up, it would be about the weight of a sheet of paper. So the whole helicopter weighs about 4 pounds, but yet it's able to, lift itself up and fly around. And we did many tests of the legs. The legs are springy so that if we bounce a little bit on landing, they don't break, and they're very stable. They have a wide stance so that if we bounce a little to one side, we can recover. And it's a very tough system. So we spent a lot of time. We had some advanced partners that helped us out, that designed it so that it could be strong and light at the same time. So we're very confident that whatever Mars can throw at us, we'll be able to handle it.
Well, in your confidence, we trust. So we are going to take a couple more questions from the audience in just a moment for both of you. But I have one final question for you. Is this part of the dream of working at JPL? You get to be a part of a unique, first of its kind mission. Is that why you come to work at a place like this? And Tim, why don't you take that one first? We're going to pull up image 8.
Well, sure. It is definitely a dream. I grew up in small town America, and I grew up reading all the National Geographic issues about the Voyager probe and all the different outer planets that it visited. I love to consume all kinds of astronomy books, and I was generally a computer geek, so all this stuff came together really well. And I was able to get a job out of college at JPL and do really exciting things, which is really culminating in this chance to do a first of a kind thing on Mars, which is to fly a helicopter, which has never been done before. So sure, we're very nervous, but we're confident in our helicopter, and we're excited to go, and we're really looking forward to it.
And how about for you, Farah? Is this part of the dream of working at JPL for you as well?
Absolutely. So for me, my story is that my first summer at JPL was the summer of 2012, and I was an intern during graduate school. And the summer of 2012, for those of you who are space fans, is the summer that Curiosity landed on Mars. And I still remember that moment in the auditorium. It was like late on a Sunday evening, and I was super nervous with my friends watching the landing. But what was so incredible as an intern is to be on lab and to see these incredible people achieving the impossible, right? Like, who sends a massive rover to Mars and lowers it from a sky crane on the surface of Mars? And who's crazy enough to do that? Apparently people at JPL. And I thought, I want to be one of those crazy people. And that is really, when it started, I knocked on every manager's job with my door with my resume. And I was like, I want to work here. This is what I want to do. I want to be part of a team like this. I want to do these things. So I was lucky enough to get a job back in 2014, and this is my second Mars mission. But with this one, it's really coming full circle, right? Perseverance is sort of the big sister for Curiosity, and it is that next big mission. And it's so cool to be able to say that I am now part of the team that's making history, right? Like, I'm part of that team that's doing crazy things on Mars. And it's super humbling too to have like come full circle that way and be part of that team. And what's special with Ingenuity is, with other missions at JPL, we've had other rovers before. So often when we have problems, there's always someone to call. We can call the person that did it on Curiosity and ask, like, we have a similar problem here. Can you help me? Not the case with Ingenuity. No one's done this before. There's no textbook. There's no one to call. We just got to figure it out. And that is sort of like the best piece of engineering right there, right? Like we have to figure it out. We figure it out as a team. We come up with creative solutions, and we're the ones writing the textbooks, right? And eventually, I can't wait one day when, hopefully this all goes well, and one day we'll be the ones getting the phone calls. We'll be the ones that people are going to reach out to when they want to fly the next helicopter on Mars.
Really incredible, groundbreaking work that you both are doing. And I am sure that social media is lighting up with questions. For those of you that are still watching with us, please make sure you put those in the chat, and our social media team will bring them to us as quickly as possible. We'll answer as many as we can. Sarah, how's it looking out there?
Oh, there's plenty. There's plenty. Can I ask one right now?
Please.
Now I got to clear my deck here. Great. Okay. I don't know if his name is Brian or Brain. I kind of hope it's Brain, but it's on LinkedIn. This is a question for you, Tim. How did you simulate the low gravity and low atmospheric pressure during testing on Earth?
Well, JPL, along with being a place that has cool spacecraft, it also has cool ways to test things. So there's a chamber at JPL. It's 25 feet across and 70 feet high, and they've used it for years for spacecraft to pump down and pump out the air to get it to either a pure vacuum, or in our case, we pumped it down to 1% of Earth's density. So that's where the helicopter will fly. So that's how we're able to get the equivalent atmosphere. And we had some very clever engineers that came up with a design. We called it our gravity offload mechanism. And it was a special computerized system that had a tether or a big cable that would come down and attach to the top of the helicopter and would literally pull it up in a way that would simulate Mars gravity. So that way we had this chamber that could both simulate Mars gravity and also the air pressure of Mars. And so that's where we did almost 3 years of testing to get the helicopter ready for Mars.
That's quite a bit of dedication. I mean, you've already showcased that tonight, how dedicated you've been, but 3 years of testing, that's quite dedicated. Sarah, we've got time for a few more questions.
Great. Excellent. Okay. This one is for you, Farah. Pedro on LinkedIn. So a lot of questions from LinkedIn tonight. This is great. How will Perseverance track Ingenuity in the sky? Is there a beacon or object recognition?
That's a great question, Pedro. So actually what we do is that we can localize the helicopter, and we're going to keep track of where it is on the ground. And then based on what we think the flights are going to be like, we're going to set our field of view wide enough on our cameras to be able to catch the flight. So when we drop off the helicopter, we'll know exactly where it is, and we'll have, we keep really good maps of Mars when we drive. So we'll have a map of where we are and where it is. And then as we drive away from it, we'll be augmenting those maps and relocalizing using images every time. So think of it as like I've set a pin on a map and I try and point back to it. And based on my images, I can sort of adjust a little bit what the error might be, in my position, or what I think my position might be with the helicopter. So even at 100 meters away, we'll know where the helicopter is, and we'll be able to image it before its flight, so we know exactly where it is. And then the morning of that first flight, for example, we'll point all our cameras at it. We have multiple cameras, and we'll wait eagerly. And we're even going to take a video, hopefully, of the flight. And then we should see that helicopter in our field of view. And then when we're done and it lands, we'll be able to relocalize again and figure out exactly where it's landed.
Okay, and I've got one for Tim here. Oh, sorry about that. Didn't mean to jump out there, but I'm going in. I'm going in, Nikki. Great. Kirk on Facebook. I thought this was for you, Tim. Does the helicopter have any smarts to adjust if its flight model is not exactly what it's discovering on Mars? Basically, can the helicopter make adjustments or learn along the way?
Well, certainly the software is, we did a lot of testing on the flight algorithms. We have a very talented guidance and control team, and they built the software to follow a set of waypoints. So before the flight, we get together as a team and we plan where we want the flight to go. And then the software on board will take those waypoints and fly that trajectory. And the software has the built-in smarts to adjust to environmental conditions it might encounter, like gusts of wind or, just deviations in the flight path. It's very well designed to bring it back into alignment with the path that we had planned for it. So that was part of the new development that we did for this project, is they designed all new, brand new algorithms that can handle the Martian environment, plus this mission that we gave it to fly along these trajectories and do what it needs to do, because it's not only flying based on an inertial sensor, it has a camera system that points downward. We're taking pictures 30 times a second, looking at features inside the camera, the image of the camera, and then track those features from frame to frame. And that's how the helicopter is able to know which direction it's going and how fast, along with the inertial sensor and even an altimeter. So it's a pretty sophisticated little robot for finding its way across the landscape.
We have time for some more questions, Sarah, so feel free to ask a couple more.
I was waiting for you, Nikki. Okay, this is also for Tim, because this is a little bit about the helicopter team. And so I know that you've been on the helicopter team for a long time. So Rhonda on Facebook is wondering, first of all, how big the helicopter team is. And then sort of a related question from White-tailed Jedi on YouTube is, who gets to pilot the helicopter every day? How do you choose?
Oh, that's a great question. So we had a team, I would say at our peak, we were probably 30 or 40 different people all bringing different kinds of talents to the table. I'm here because I'm representing operations, but there's many other talented people on the project who did mechanical design, the thermal design, the power design. And when you mentioned the pilot, our chief pilot, Hovard Grip, is a very talented guidance engineer. He even flies planes for fun. So he's a naturally gifted guy for doing this. And he's the one with his team that are going to be planning each one of the flights. And so that's how it works is the guidance team gives me the path they want to follow. We enter it into a series of commands. That file of commands we give to Farah and her team, and they beam it up to the rover. And then the rover sends it across to the helicopter and executes it. And then we get to wait until we see the data as we chew our fingernails to the bone.
Okay, here's another question. Why don't you try and take this, Farah? Gabriel on LinkedIn is asking, so how does communication between the Mars instruments get affected by the lack of the magnetic field that is on Mars? And does the solar radiation affect the communication between the helicopter and the rover?
So we obviously the environment on Mars is different from the one on Earth. But one of the things that we did on Earth before we went to Mars is that we actually tested that communication. We do something called electromagnetic interference testing. And so we put the rover in a special chamber that's quiet like Mars, or as quiet as we can get it. And one of the things that we had to do actually is we had to figure out if there were any instruments on the rover, like when we're changing or switching things on the rover, whether any of that magnetic noise that's created when you use those instruments might affect the link between the helicopter and the rover. And so, we're talking from the helicopter to the rover using a radio that has a certain signal, and we want to make sure that there's not noise in that signal created by other instruments on board. And we actually found that there's a few instruments that, for example, if we're moving our motors, that creates just enough noise that we can lose communication with the rover, or we can lose packets. So that's why we do that kind of testing before we go, so that we kind of understand the behavior. And then when we get to Mars, we're going to sort of restrict the usage of certain things. Like we won't be moving our arm all over while we're talking to the helicopter, so that we know that we can get a clean signal that way. So yeah, it's definitely a test that every single spacecraft goes through. It's one of the key tests that we do before launch to figure out what's compatible with what, and make sure that we can successfully communicate with our helicopter in this case.
Okay, do we have time for another one?
Yep, we've got time for another one.
You got it. Ron on LinkedIn is asking, will the helicopter attempt to land atop higher elevation features, or typically always return nearby the rover? I guess that's for you, Farah.
So right now the plan is to land at the same place. So what we've done, or what we're doing on Mars right now, is we're trying to identify a flight zone. So it's an area that's about 30 meters across and about 100-meter long, and that is going to be our stage to play on. That's where the helicopter is allowed to fly. And within that, there's an area that that we're going to identify or try and find that will have, we're looking for a flat area with hardly any rocks, where the helicopter can land. That's kind of its like landing pad, right? Like, so if you have a helicopter on Earth and it can only really land in that flat area with a big H on it, that's going to be our helicopter on Mars. No big H, but we'll have our area where we're going to be able to drop our helicopter and fly to and from there. So the goal is to always return to that home base, and then from there do increasingly more complicated flights. So at the beginning we'll just go up and down, and then we'll go across, and then we'll see. Maybe the helicopter team will get sporty and try to break free of the current plan. But for now, we're planning on landing at the same place.
Break free of the current plan. That's brave. I like that. I like that.
Getting sporty.
We've got time for just a couple more questions, probably about 2 more.
Oh, okay. All right. Angelica from LinkedIn, she's getting it. This is for you, Tim. So what is the actual flight goal of the vehicle? Is it flight time? Is it distance? And is there a particular forward velocity that you're looking for with the helicopter?
Well, since this is a kind of a new mission, we've never done this before. The primary objective of this mission is to characterize what it's like to fly on Mars. So we're going to be doing, as Farah said, a series of these increasingly aggressive flights, and we take lots of data during those flights, and we analyze that data on the ground to see how it performed. And then that's the kind of data that will feed forward into future possible helicopters that can do more and have greater capability. And so that's really the objective, is to test how well it flies. And so we'll be doing these increasingly harder flights to stress the system a little more each time and see, how the data comes back when we do those flights and how it responds to those various things in the environment like wind and altitude. And we're going to fly at about 5 meters high. We're a little bit limited by our altimeter, how far down it can see, and the camera system. So it'll be about 5 meters high, and we'll be flying 2 to 3 meters per second horizontally when we do our horizontal flights. So it's not going to exactly buzz the tower, so to speak, but it's going to be, it's going to be faster than a rover. That's one of the promises of a vehicle like this, is that the rover potentially could see a feature in the distance that it thinks is very cool, but it could take days or even a week to get there. And something like a helicopter could fly over there in just a few tens of seconds and analyze and inspect it. So that's part of what this mission is about, is to do this groundbreaking work to see how well it performs on Mars, so that future generations of helicopters can do even more cool things.
I like that. Even more cool things in the future. And speaking of things in the future, we have one final question, Sarah, for our speakers tonight.
Okay, let's take it from Facebook. From Matt on Facebook asks, will imagery from the helicopter be used to help Percy navigate the Martian terrain as it makes its way to the Delta?
I can take that one. So
sure, thank you. I should have said that's probably a good one for you, Farah. Got the Perseverance connection.
In the nominal plan, no. So what we're learning, again, as Tim just mentioned, right? Ingenuity is paving the way for future helicopters, for future missions. We want to demonstrate that, that helicopters can fly on Mars. And by the way, rovers started as technology demonstrations too. That's where we started, a small team came up with a small rover on Mars, and that showed that we could drive on Mars. And now look what we're doing, right? So we're really hoping that one day Ingenuity will be that stepping stone also for bigger helicopters. But in this case, the area that Ingenuity is flying over is one that we've already imaged. We actually wanted to assess that area to make sure that it was safe, so that if Ingenuity needs to do an emergency landing, for example, we know that it's a safe area, that it doesn't have big boulders and things like that. So again, at least per the current playbook, and who knows what the team is going to decide to do once if we are successful with those first few flights. But for the first few flights, at least, it's going to be an area that we've already imaged. But it definitely is going to be really interesting, right, to look at the path that it takes and the images that it takes and compare that to what we know about the surface. And again, that's going to help us learn about what it's like to fly on Mars and what it takes. So it's definitely going to be something that we're looking forward to.
Great ability to develop new technology. Thanks for those wonderful questions to all of you out there, and thank you, Sarah, for presenting those to our speakers. But unfortunately, that is all the time we have today for questions. Please join us next month for our lecture and Earth Day special, Science on Ice: What Ice Says About Past, Present, and Future Climate. I want to thank our speakers, Tim Canham and Dr. Farah Alibay. Thank you so much for joining us and discussing this very exciting topic. Also, big thank you to our wonderful questions co-host, Sarah Marcotte, and everyone working behind the scenes to make this possible tonight. And to all of you watching, thank you for taking the time to join us every month, and thank you for your wonderful questions. If you've missed one or would like to revisit any of our Von Karman talks from the past 5 years, they are available on JPL's YouTube page. Thank you again, everyone. Be well, have a wonderful evening, and we will see you in April.